seems to be working okay. And so my goal is to be not the first person, or not the person that falls off the stage, or in some other way gets everything here on Twitter and more attention than it probably deserves. So hopefully we'll be able to do that. So this is X9.143 and PCI pin compliant key blocks. This is a technical presentation, whereas a lot of the talks here are not nearly as technical, and they asked me to keep this short, brief, concise. I've got it down to a tight 60 minutes, so we better get started. All right, so this is the agenda. You can see what's on there. I do want to mention that I've abbreviated most of the names to the names you're familiar with, TR-31, and introducing X9.143. What you might not know is there are 3 versions of TR-31. Dates back to 2005, and those are the versions and the full names. ASC X9 TR-31, ANSI X9.143 is the new document. So I'll start off with what are key blocks. A key block is a set of attributes, a key, which is really just a string of bits, and a wrapping method, which includes integrity protection and encryption. Now, why did I start with attributes? To me, the attributes are the important part of the key. The attributes say what the algorithm is. Is it an AES key? Is it a TDES key? Is it an RSA key, right? And the attributes say, what can I use it for? So to me, the attributes are actually more important to know than the key. Of course, the key is important. That's the one doing the work. But the attributes make the key what it is instead of a string of bits. Now, wrapping method is not just encryption, right? We all, in standards, use the term integrity protection and encryption wrapped up in the wrapping method. So when we say a key is wrapped in a key block, that has a special meaning. It's not encrypted in the key block. It's wrapped because it includes that integrity protection. Now, where does PCI mention key blocks? They started out in PCI pin 18-3 in 2014 and PCI pin 2.0. And the effective date for people to have that rolled out was 2018. That was for all phases, right? It didn't have phases. So in 2017, that was updated and split into the 3 phases that everyone knows. And that was adjusted later into the dates that you now see. Now, there was something I want to draw your attention to. There was a key block supplement that was published, and that was just recently updated in the middle of the year. So you'll want to go and download the latest key block supplement. Now, in January 2023, there's an important date to know because that is the date that unreviewed proprietary methods will be sunset. And I'm going to come back to what that means a little bit later on. So we talked about what are key blocks. We talked about where PCI mentions key blocks. What are valid key blocks according to PCI? Valid methods are TR-31, surprise, surprise. That's in the title of the talk. And this definition is expanded to include X9.143, the standard, but there are also coverage for equivalent methods. Now, what's an equivalent method? That's a very complicated topic. But an equivalent, to judge an equivalent method, you can't just write to PCI and say, I say it's equivalent, right? You need an independent expert who has a serious set of credentials. There's not very many of these in the world. I'm not one of these people, sadly. It's a very special group of people, but you find that person in that group, and they will review your proprietary key block, and now you are judged equivalent. This is fine. You can use proprietary key blocks alongside X9 TR-31 or 20038 as equivalent. I will say, as the marketing statement for my company, that we have one of these independently reviewed proprietary key blocks. So, all right, marketing over. And I didn't put it on the slide, so I got under the door. All right, now, the big question there, I think you know the answer. Do I need to migrate from proprietary key blocks to TR-31 or /X9.143? The answer is no, you don't need to migrate, right? But you need that independent review because your PCI pin auditor will ask you for that. So let's get a little deeper into equivalent methods. I've got a summary there at left. Really, you need to be able to separate the keys according to the data they protect. If I have a PIN encryption key, I need to be able to tell that from all my other data encryption keys. That's really what we're here doing in PCI PIN. So that, all right, makes sense. You also want to hide the key length. Guess what? Not even TR-31 does a good job of this. You need the key to be for one algorithm. Remember I said before, a key block defines what the algorithm is, right? Is this an AES key or is it a TDES key? There's also some requirements there about rejecting a bad key block. If the key block is corrupted or if someone has messed with it, you need to reject that before you use the key. And you don't want to use improper wrapping methods, such as those that include a variant technology, which I'll get into more detail, and that's getting very technical. So, oh, I'm sorry. I had a question at the bottom, does TR-31 X9.143 have all of this? And that's a complicated answer. So to answer that, I'm going to get into a quick history of TR-31 X9.143, and I'm not going to read to you everything on the slide, although it would probably be a help. I'm not sure you can read that text at the back of the room. But I do want to point out a TR is a technical report. So that will become important later. And a technical report is not the same as a standard. Now, in 2005, the first version of TR-31 came out and introduced the A wrapping method. And it was only for TDES, only for DES and TDES keys. There were 3 optional blocks, which were not very usable because people didn't know the format. There were no defined layouts. So the 2005 document was very helpful, got people going, but there's definitely a lot of work and ground to cover. 2010 made this picture a little better, added a good wrapping method, the B wrapping method, but it was still focused on DES and TDES. In 2017, ISO 20038 came out, which added AES key wrapping. But there's still no layouts defined for optional blocks. In 2018, ANSI, the US organization, took back the contribution from ISO and put that into TR-31 2018, but didn't do a great job. They changed the way you represent HMAC keys. So they're not actually compatible. The way you represent an HMAC key is different in ISO 20038 from TR-31 2018. So that's another pitfall. Now, we do come to X9.143 in 2021, and that is a standard. One thing that we do have there is a deprecation of the A wrapping method, and I'll get into a little bit about that in a minute. It notes that the key size should be hidden and that unknown optional blocks should be rejected. So security first, let's talk about the wrapping methods. The A and C wrapping methods are actually exactly the same. The reason that the C wrapping method was introduced is just purely historical, and it wouldn't help the length of my talk to get into that. But the wrapping method does, it has an encryption step and it has a MAC step. And so the way we kind of talk about the difference between the A wrapping method and the B wrapping method is encrypt then MAC, and the B wrapping method does MAC then encrypt. So the encrypt then MAC method that A uses uses a variant calculation. So you start with a wrapping key and you XOR it with a constant value. That's the variant method. It's very simple. Unfortunately, you can XOR that constant back out because it's published. If you have broken the wrapping key, you can get the key you started with. So that's why the variant method's not great. The other problem with the A wrapping method is that it violates CVC mode, which states in the NIST document that the IV doesn't need to be secret, but it must be unpredictable. And the MAC IV is the header. The header is there clear for everyone to see. So you really have 2 problems with the A and C wrapping methods. Now, I've got some discussion of the attacks there, but I'm going to skip ahead. But basically, if you break TDES, you can reverse the variant and get the KK. And so that's the main problem here with the A wrapping method. And so we come to the summary there at the bottom. Pitfall number 3, these methods aren't really compliant. Oh, wait, I went too far. Sorry about that. I think I just hit it twice. Anyway, so the B and D wrapping methods. The B wrapping method is a TDES wrapping method. You're using a DES wrapping key. The D wrapping method is very similar, but it's AES-based. Now this does MAC then encrypt, and you start with a one-way key derivation using a NIST published algorithm, and this is CMAC-based. So you start with your wrapping key, and then you do 2 derivation steps that are not reversible. It's a one-way function. So these encryption keys and MAC keys, you cannot, if you attack the key block and you recover one of them, you do not get the KK. You don't break all the other keys wrapped with that KK, like you do with the A wrapping method, right? You only get one key, and that's what we want. One key exposed if you do that break. Now, the CBC mode encryption is good, and you see a much better protection against those attacks. So this is a summary of the pitfalls. I've gone through the first 3. Pitfall number 4 is that the padding was not required in TR-31. So the padding, again, is in the payload. It hides the length of the key. Let's say you have a short TDES key or a short AES key, 128-bit AES key. You want to pad the length of that key block so that it looks like a 256-bit key. And that way, an attacker can't tell where your short keys are, right? Well, if I'm an attacker, I want to attack the short keys. I want to attack the weak keys. Maybe the key that protects half your business is a single DES key. Do you want the attacker to know that? So you want to hide the length of the key in the key block. That's the idea. So TR-31 never required that you hide the key length, but PCI does, right? PCI does. That's in the equivalent method. Pitfall number 5, TR-31 allowed numeric identifiers for proprietary use. So you can have a TR-31 key block where the first character is a number. That makes it a proprietary key block. If that is, and the problem with that, you don't know the wrapping method. So it could be anything. You really don't know. So what you want to do then is you have some questions to ask for your implementer of what are the security properties behind this numeric key block, this proprietary key block, and then of course it would need to be reviewed for equivalence because it's that one number at the front that makes it proprietary. All right, but the biggest pitfall with TR-31 is that it's a technical report. You have agreement between parties that implement it. That's interoperability. There's nothing in it that's enforceable because it's not a standard. So I said on the last slide that there are questions to ask your TR-31 provider. These include, does your device actually enforce these? TR is technical reports, not a standard. You're not required to enforce those properties. X9.143 as a standard, right? X9.143 to the rescue, it has a shall statement. Your device shall enforce that this key is only used for PIN encryption. TR-31, there's nothing to enforce because it's not a standard. Now, another question to ask is, and this is very technical, but that padding that you put in the key block to hide the key length, it's supposed to be random bits. Now, one question to ask a proprietary provider, someone that's implementing TR-31, are you using random bits? If you're not, then I can predict very well, what a padded key block is like. You've reduced the search space for the attacks. All right, so X9.143, here are some features of what X9.143 is introducing. And I think there's a lot of interesting stuff here beyond compatibility with TR-31. So the byte 14 of the header was reserved. And what we've done is add context there. So you have a definition of that key block for local or transfer context. TR-31 was introduced for exchanging keys between parties. It was never defined as a local key block that you would use with your HSM. It was defined as a key for exchange between my business and your business. So now in X9.143, along with standardization, we've defined a bit that you can set and say, this is the key I'm going to use with my HSM. And so you can also, if you think about it, you can run reports. Here are the keys that I've been exchanging with people. Here are the keys that are defined for use locally with my HSM. So I can tell them apart. It's ASCII text in the header. Very easy to run a report on. You can eyeball it. All right. Bytes 5 and 6 are the usage bytes. There's several more usage bytes identified, and I'm not going to explain what all of those are. The slides, I think, will be made available, and you can go back and look at them. So that will help out there, but I'm running low. I did want to get to optional blocks, and I've mentioned before that optional blocks have been a feature of TR-31 since 2005, but they were not used hardly at all because they didn't have defined layouts. And I said that X9.143 has defined those layouts, and that means as it's a standard with a defined layout, that makes them interoperable. Right? As these get deployed in the ecosystem, you can all take advantage of these features. Right? And of course, it helps if people ask for those features of your devices. So what are these features? A key check value for the key itself and a check value for the wrapping key. So you have bound to the key what key wrapped it. Right? You don't have to keep track of that somewhere else. And you have bound to the key what should the key be. And you can verify that yourself. You can also bind a label to the key. You're used to labels in your key management systems where you pass in the label that refers to the key. There's no binding between them, right? So I could swap them. But with this optional block, the LB optional block, the label optional block, you can bind it to the key, and if someone has changed the label, if someone has changed the key that maps to that label, you'll get an integrity fail and get kicked out, right? There's also time stamps on the key blocks. So again, you want to know how old is this key? An optional block can carry that, contain it. It's bound to the key, so if someone messes with it, you'll know, right, because it'll fail. So you get a time of creation for the key and a time of creation for the key block, and these may be different. If I'm exporting a key, that key block was created at a different time from the original key. So that's a very useful feature. You also have type-specific optional blocks. You can put in the duck-put features, the base key, the base derivation key identifier. You can also put in extended derivation control for your keys that you don't use with duck-put. Sometimes for EMB or other use cases, you have keys that can derive to multiple different paths, and you want to control those derivations tightly. And so you can bind that derivation control to the key itself in the key block. And then the last one there is the HMAC optional block. Now, for those of you that know HMAC really well, your definition of the strength of the key is a little different from an AES or a TDES key or an RSA key where you just count the bits. Here's the strength of the key, right? 128 bits, that's the strength of the key. HMAC, you start with the count of the bits, and then you hash the key. And if you're using SHA-1, the strength of the key is very different. Even if you have 2,000 bits for your key, if you hash it with SHA-1, the resulting strength of that HMAC key is very different than if you use SHA-256 or SHA-512. Takeaways. So let's go back through the pitfalls. With X9.143, we get to cross out some of these. We have layouts for the optional blocks. The ANSI wrapping methods are deprecated. They're still there for interoperability, but they're deprecated. They really should not be used in new solutions. And we can cross out number 5 because your numeric identifiers for proprietary use, they're not compliant with the standard. And pitfall number 7, it wasn't a standard, now it is. Okay, that's a gimme. But there are still a few pitfalls that aren't resolved. There's this little compatibility problem with ISO 20038. There's the problem with padding the key to obfuscate the key length. And there's the problem that single DES keys are still supported. There's no restriction in TR-31 or X9.143. There's not a restriction by type of key either. So although it may sound a little strange, you can define a single DES KEK in TR-31, and that's compliant with X9.143. It might not be compliant with PCI, might not be something you can actually use on your HSM, but in X9.143, you could do it, and you could say it's compliant with X9.143. Now, TR-31, as we've gone over, has a long history, not a standard, has pitfalls that we just went through. X9.143, it's shiny and it's new, so it's a cool thing, right? There's a couple pitfalls remaining. The audit, it is an audit target with shall statements, so you can scan it for shalls, come up with a checklist. Local context is added. There are new key types and attributes. And there's really a lot to mine there that you can use for your applications. And let me go to the last one. I do want to end by saying thank you, everyone that came and stayed for a very technical talk that dealt with bits and bytes and something you don't see often at a conference. But and there are some where am I, where do I work, IBM crypto, and HSMs. So again, thank you very much.